So very briefly, these might seem obvious, but in a lot of control tasks, you want to identify what it is you're trying to control. And obviously in this system, that's pretty easy. We're trying to control the position of that needle. But it's not, sometimes it's more than one thing that you have, more than one process or more than one variable rather that you're trying to control. So that's one of the first things you do. You also try to identify what we call disturbances. And the control system, a disturbance is any input that's to the system that's not being controlled. That, for example, on that needle, where I'm using it here, I have a ceiling fan running, and you can see that it makes the needle oscillate sometimes, and there's a little bit of fluctuation if I have that fan too high. So that torque that's being exerted on the needle, to make it rotate and have some fluctuations, that's a disturbance, right? So anything from outside the system that causes the controlled variable or the system, but it causes changes in the control variable, that's a disturbance. And you also obviously want to identify which of those inputs can be manipulated and controlled, and then choose sensors that can control, that you can use to identify, to ideally measure the variables to be controlled so you can feed them back. And again, there's other tasks in the control system, choosing actuators, power conditioning, something we don't need in this system because we're driving directly through my deck. As I mentioned before, it's a low current device, so we can drive it right out of the output of our DAC system. Sometimes controllers also need some logic. We won't get into that, but a big part of what we'll talk about is tuning, and both tuning and stability analysis end up being a big part of what you do in designing a control system. And we'll just give you a flavor for that. I'm not going to talk too much about stability analysis, but you'll practice tuning when both in the simulation and in lab. You'll spend some time doing that. So here's your kind of standard, kind of canonical, if you like, closed loop control diagram. This is something that I think you should be familiar with as an engineer. And there's some common terminology. The plant is the device or the system or process you're trying to control, and so the input to the plant is the control input, right? And we'll use the symbol U sometimes. Again, terminology changes, so it's not important. But that's your input coming into your plant, your system. So this is our analog meter. We have a voltage in, and data is the output, and that's our control variable. So the plant is any system to be controlled. The controller is something that generates the inputs to the plant so that you can achieve a desired objective. And then you have a sensor. So obviously this is what we've built already as our measurement system in the control for this meter experiment. So this is actually, this path defines measuring theta using vision and then feeding that back. So the reference is your desired positions, right? So there might be a motion plan of how you want to position that needle. This could be a speed input, it depends on the temperature, depending on what kind of control system you have. This block again is a summer, so the difference between the reference and the feedback signal. Remember, these have to have consistent units, right? So this is theta. If this is theta, this is theta. So you have an error in theta. And that error is fed into the controller. The controller is looking at that error and then making decisions according to some logic, some process, some defined transfer function, what the controlled input should be, right? So be familiar with that. And this is also something called a single input, because you have one input, single output, or CISO is a common term. So single input, single output controller. There's multi-input, multi-output controllers when you have very large systems, right, where you might have more than one input and more than one output that you're trying to control. So we'll mention this on occasion, but why close the loop? Some of the advantages is we talk about disturbances. So one of the things that closing the loop does that an open loop control can't do is that you can't reject the influence or really minimize the effect of disturbances. So that's what you're trying to do. You're trying to make it so that any disturbances, remember those are inputs that are not controlled, can be minimized, the influence. Also, you want to, if parameters in the system change, you still want your system to perform well. Like in a cruise control, for example, if the number of if the mass of the vehicle changes, you don't want you don't want the controller, the speed control to change, obviously. So those are the two big ones. You provide rejection of disturbance, and also make the system insensitive to parameter variations in the system. The other thing that a feedback control can do is you can use that error signal to dynamically track. We usually talk about two kinds of controllers of this type. Usually you have something that's called a regulator. And usually a regulator refers to, you want to keep something at a certain spot. So let's say we wanted to put the needle at a certain position and leave it there. And so you're telling go to 20 degrees and stay at 20 degrees, and no matter what disturbances it has, the controller's fighting to keep it there, right? That's a regulator. Keep it at 0, put it at a certain position, hold it there. That's a cruise control is like it's a speed regulator, right? You're trying to stay at that constant speed. Or you might also have a tracking control system where your reference signal now changes according to some prescribed signal over time, say, and you now want your control system to track that system. So you have regulators and trackers. The control system, closing the loop, also has the effect of improving accuracy, obviously, and extending the bandwidth. You can, if you have hopefully the power capability, you can extend the ability of a system to perform over a wider frequency range, say, and also dynamic range. One of the disadvantages of feedback control system, aside from cost, you're adding sensors, you're adding more complexity, and you're having to design a controller and so on. So there's cost, but the critical thing is one of the influences of closing the loop is that you now make it possible, if you don't tune it correctly, that the system could become unstable. So whereas you might have initially had a system that was stable, you might make it unstable through the control that you design. So that's why so much time in controllers is spent trying to guarantee that it's stable and designing it properly. Okay. Obviously, you always use a negative feedback. It's stabilizing. If you use positive feedback, it's going to be unstable, right? We all have seen examples of that with microphones and so on. Okay. So when you have that closed loop control system, we populate each one of those blocks with these with transfer functions, with actual functions, and the standard is that these are some kind of functions of S. You can have more complex functions in a controller, but the simplest type these are all linear type transfer function elements. But we know that we can construct block diagrams with elements here that are not linear. So, but this is the standard linear elements here, and your controller description is and when I say here's a function of S, these are S domain descriptions. These are again the signals on the lines, but these are functions, transfer functions. Okay, so one of the things that we seek to do here is we want to find, if C is our control variable, we want to know how does C depend on the inputs of the system. We have disturbances that can come in here, right? You have the output from your controller, and then there's something disturbing it, and then it become an input to the system. And then we also have the other input. There's no other input. This is the only output. And then we have the reference input. So we want to see, how does C depend on the two inputs? One is the disturbance, and one is the output. So this is what's called a closed loop transfer function. And this can be derived just directly from this block diagram. Okay. And once you have that, then you can put these specific functions in there. And actually, if you look at this, remember this, each of these is a transfer function. The denominator here tells you a lot about the performance of the system. So The G sub P is the transfer function of the plant, which is what we've already derived in the model part. The GC, we're going to look at some examples of these. These are the controller transfer functions. And then H is the measurement system transfer function. If you know these, you can change them. Well, maybe you can't change the plant, but maybe you can change the controller, and that's the whole purpose of control design. So you have opportunities here, both in the controller and in the measurement, to change the overall performance of the system, which is determined by the denominator in this transfer function. And that's how control design works, is to find the right controller that gives you the performance characteristics that you want. So why derive a closed loop transfer function? Well, I kind of discussed that just now, but now you can prove some of the properties and you have a basis for making decisions. Let's move on now and introduce the basic control actions that you put in that G sub C transfer function. And this is something that I think is good for any all engineers to know walking into any kind of environment where you're using controllers. This is the most fundamental type of control actions that you might use. And so I'm going to talk about each one of these. You have the proportional, the integral, and derivative, and they're self-descriptive, right? And then you can combine them. So you can put a proportional action together with integral, and you have what's called a PI control, or a PD. You have proportional and derivative, and then you use all three together. That gives you the ability to have proportional, integral, and derivative action. And what you're doing is acting on the error, right? So what these controllers do is they look at that error signal between your reference and your measurement, and it gives you a control action, right, that tries to basically minimize that error, right? And so the proportional action obviously looks at the error and gives you an action that's been proportioned to the error, and it tries to reduce that error, and we'll look at that. If you understand the PID and how it's put together, it gives you a good understanding of most controllers that you're going to see in practical applications. So it's worth kind of having a good understanding of that. Just to show you the basic idea, let's say of proportional control, when you have a talk about proportional control, that G sub C function now is just a constant. So that means, well, my control action is just in proportionally related to my error, right? So here's your control. The U that comes out is just Kp times the error. Show these in two, and this is kind of time domain, this is S domain. Kind of mix them a little bit, but you get the basic idea that the control in the S domain is in proportion to the error. If you insert that into that closed loop transfer function, say you don't have any disturbance. So here's a basic closed loop control. Let's say you're trying to control the position of this mass, right? So this is, let's say X of this mass here. So let's have a transfer function that relates the position of this mass to some force that's applied on this mass. Let's say that's not shown, but that's going to be the control action U, right? So X, the position of this mass, over U is the force on that mass, and that's what I'm applying there. So let's say I know this transfer function. I'm just going to put there's no disturbances on here. I'm going to put a proportional controller here, right? And this should be a negative there, and it's a positive, right? This is my reference input. Is I'm saying I want to be able to position that mass at a certain point. And I'm going to assume that I have unity feedback, or an ideal. This is my measurement function, right? It's just one, saying that I can perfectly measure that, and so there's no difference between what the actual variable I'm controlling and the measurement. So the measurement's perfect. That's an assumption, but it's good enough for this application. And so when you close the loop, right, doing this here, now I want to know, how does the output X sub C, the control position, depend on where I want to control, and I can derive that transfer function just by going back to that closed loop transfer function formula and putting in the values for the GC, the GP, the H. When I do this math, you see that you get this transfer function, you get a nice second order system, and you can see the effect of this gain here. Remember, this value is what you can now play with, this control gain. The effect of it is to make the system look stiffer, so you're kind of changing the overall characteristics of the system right now. by increasing K, you can make it stiffer. But what you're also able to do now with this system is track. So as I change X, you know, it's gonna force the position to go to that. So you're gonna get position control, right? And by the larger the K is, the more stiff it is. The smaller, the less stiff, and it's gonna have more. It's going to be a softer kind of system. So you can see how that gain has kind of a physical effect too, right? That's proportional control. So forming integral and derivative control is self-descriptive. There's two different, you'll see these two kind of described in two different ways. Sometimes your control action due for the integral is related to a time, integral time, and then there's also a constant, and so it might be in this form. So you have not only a gain here, but also a t sub I, and then also in other times you might see that there's just a constant k sub I, and it's written in this form here, and there's no t. Similarly, the derivative control, you might have a t sub d, and sometimes you might have just a k sub d. So I summarize these down here. Sometimes you'll see the PID where I put all three together now. Sometimes you'll see just one proportional gain, say, and then there's they're always going to have three parameters when you have PID control, but you might have just one proportional control, and then you have an integral time and a derivative time. Sometimes you'll see just three gains on the proportional, integral, derivative, and so again, just depends on what book you're reading. I'm going to show you in a second how in LabVIEW it gives you actually an option to use either one of these. They call this one academic. They call this one parallel. Okay, so once you have this control, so let's think about the PID here. Once you have this controller set up, what your job is to find what gains here will give me the overall system behavior that I like, and that's what tuning is all about. One more thing I want to show you is feed-forward control is something that can also be pretty beneficial. As we've talked about, one of the advantages of feedback control is the ability to diminish the influence of disturbances. But if you think about it, if you know or you can measure those disturbances, you can try to counteract them before they influence the system. So if you don't know them, then you're asking the feedback to do all the work. But let's say you knew what those disturbances were going to be. You could then take some of the burden away from the feedback and use some feed forward, right? In other words, use a model of the system to counteract those disturbances. And so sometimes that can be very beneficial. Let me show you how that looks. So what you do is, here's your conventional feedback control, and what you do with the feed forward, so that's R is your reference, and you know where you want to be. So the feed forward is kind of like the open loop control, right? You take the desired position and you feed it through this function, and you define an input that can counteract the disturbance or can make the system behave the way you want, right? So you can use this feed forward to help the feedback, and so sometimes they're nice to use together. You can put both of them in there. You know what this, if you know disturbances or you know dynamic effect, get the system to counteract dynamic effects before they happen, so that you don't make your feedback have to compensate for that through error. And then it makes the feedback work a little bit less. You can actually show that you can get power reductions that way. So keep in mind that feed forward is open to you as well to try to implement. Since we have a static gain, we can use that in this path, and that's something that I'll suggest you might try in the lab. One last thing I wanted to just mention is stability, and in the controls course you'll spend a lot of time analyzing systems to assess stability, using stability to choose gains, to tune, and so on. Just want to give you a definition. When we talk about stability of a system, it refers to its ability or tendency to seek a condition of static equilibrium after it's been disturbed. So you want this, we talk about stability being a system being stable. If you perturb it, it comes back to a nice equilibrium, right? And so when we looked at that overshoot, for example, we said that that was relative stability means it can oscillate away from this point that you want to go to, but it comes back, right? So when we talk about absolute stability, we say, oh, it's stable or it's not. In other words, if we perturb it away, it just keeps growing and goes unbounded. So we talk about absolute stability as a measure of whether it's stable or it's not. It doesn't say how well it's behaving. It just says, look, it's not stable or it is. Okay, so there's a difference in the terminology, absolute versus relative. Okay.